Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please go ahead and pause the video, subscribe to this channel because you're going to like the content I have and I will have in future as it relates to Python or image processing or deep learning. Now in this video, I'm going to talk about semantic segmentation of aerial imagery. And why am I doing this? Because many of you asked for this specific topic. This is not that different from semantic segmentation of microscopy images or any other type of images, because I'm going to use UNet. I'm a big fan of UNet. I've tried VNets, I tried Tiramisu network and a couple of other variants out there. The standard UNet always amazes me. It does an amazing job. So I'm going to use UNet right here. The only difference between my previous videos and this one is going to be in terms of handling the data sets. Okay, how do you pre-process it? How do you make it? How do you get it ready? Once the data set is X-train, Y-train, X-test, Y-test, you're all set. Okay, so let's start by understanding the data set here and then jumping into the code and going through the code line by line. And I'm going to share the code. Please look at the link to my GitHub repo down in the description. But let's jump in and get a quick understanding of this data set. This is not a large data set, which makes this a bit challenging. Okay, this is right out of Kaggle. I'll show you the page in a second, but let's understand the structure of the data. So it consists of aerial imagery, apparently of Dubai, obtained by MBRSC satellites. Okay, and they're all annotated pixel-wise, like for semantic segmentation, and there are 6 classes. And these 6 classes are building, land, road, vegetation, water, and whatever that's unlabeled. The problem is there are only 72 images. And that's it. Okay, there are only 72 images. And these images are divided into different folders called tile 1, tile 2, tile 3, tile 4, 5, 6, 7, and 8. And each of these tiles has 2 subfolders, images and masks. Okay, just with different images names and then masks, corresponding masks. Okay, so far so good. And all we know is hex code for each of these, right? 3C1098. I'm going to briefly talk to you about what this is. In fact, I made a video in the past as part of my Python tips and tricks series, but I'll repeat part of that anyhow. Okay, a bit more understanding about this. Okay, so we know that these are all the labels that we have, but each of these tile folders, if you look at that, tile 1 has images 797 by 644. Tile 2, 509 by 544. This is tile 3, tile 4, tile 5, 6, 7, and 8. Each of these is completely different dimensions. So we need to do something to handle that. Okay, we need to pre-process so we can capture all the images into numpy array. You can create a list of individual numpy arrays of these different sizes. But if you're on a grand numpy array saying that, hey, I have 10 images, each of this dimension, obviously you need all the dimensions to be the same. So we need to do some sort of a pre-processing. What I plan on doing is take each image tile, a large tile, initially crop it to a size that's divisible by 256 by 256, and then extract 256 by 256 patches. Okay, so that's my approach. And these masks that we are going to see again in a minute, they're all RGB color masks, and the information is only provided as hex color, right? 3C1098. I hope you know how to read this. If not, again, I'll briefly explain that, which means first we need to convert this hex into RGB value so we know exactly what value corresponds to what label. And then RGB is not useful, right? In our case, we need to convert that into one-hot encoded somehow. So the way I plan on doing is convert RGB into integer values first, like 0, 1, 2, 3, 4. So it's easy for us to see, and then one-hot encode it. Okay, why do we need to do one-hot encoded? This is a multi-class problem. So we are going to use softmax. We are going to use something that's similar to categorical cross entropy. So we need one-hot encoded type of labels. Once we're done training the model, we obviously are going to predict or segment your images, so that those images need to be converted back into original RGB colors. If not, then the colors would be all different. Then if you're a visual person like me, then you're trying to look at the mask and your segmented image and the colors don't match. It's not easy. It drives me crazy. Okay, so this is again my personal choice to convert them back to the original RGB colors. And finally, the predicted tiles, because we are going to train the model on 256 by 256. So we take a large image when we are predicting, break it down to 256 by 256, and then predict on them. And then we have to merge them right back into an original image. And we'll see a couple of ways. One, without actually doing any blending, like cut your image into 256, 256, 256, and then put all those back together. Or cut your images into slightly larger size than 256, or cut it into 256, but then another one 256, but then there is an overlap. Okay, and then keep this overlap and then predict and then blend them in a smooth way. So when you tile them, you don't see any edge effects. I'll save that for next tutorial, next video. In this video, let's just train the model and see that we are getting a decent, decent training done. Okay, now let's jump into the code and just go through it line by line. And one other note, this is where the dataset came from. Just go ahead and Google search for semantic segmentation of aerial imagery. I'll leave the link down here, but it's easy to access this. This is on Kaggle. Go ahead and sign up for Kaggle. And look under data, go ahead and download. This is a small data set, just 32 megabytes, but which makes it a great data set for demonstration, because this is not much, right? I mean, this is not enough to get a decent trained model. So we'll see how we can perform using Unit, even with this limited amount of data. So here is the description, which is obviously I just copied directly from here. And I showed you in the PowerPoint presentation, and here it is. Here is the structure of this data. That's it, not much more information. Okay. Now, let me get into the data set right here on my desktop. So let's look at tile 1 and images. And there you go. These are all the images, and these images are of size 797 by 644, but they're all not 797 by 644. Even within a tile, there are some that are different. This one is 797 by 643. Oh, only 1 pixel. Why do you care? Well, NumPy cares. When you try to import all of these into a NumPy array, it's like, hey, I can't do that because some images are of different size. Okay. So that's challenge number 1, and corresponding masks right here. And masks have exactly the same name except with an extension of PNG. Okay, so that's what we have. So let's jump into the code. Okay, so like I mentioned, my approach is to divide these images into smaller patches. So what I plan on doing is use Patchify. Of course, you can write your own lines of code to divide images into 256 by 256 patches, but I'm going to use Patchify to actually extract smaller patches from these. So what did I do? Well, first of all, the original images are in tile number 1, 797 by 644, right? So first, I'll convert them into a size, into the closest size that's divisible by 256 by 256, which is 768 by 512, and then divide these into 256 patches, okay? I just chose this way. You can choose any other way, okay? I chose to crop the images into smaller sizes that are very close to this size. Crop, do not resize. I hate resizing when it comes to semantic segmentation. Many things can go wrong. Okay, first of all, when you resize images, that's not how your real images look like. Then you have to remember to resize original images to the same size. Okay, that's fine, you can take care of it. But what about the labels? When you resize labels, you need to be very careful that you are not interpolating, okay, when you're resizing your original masks. It often, usually there is some sort of a bicubic, some sort of an interpolation when you do some sort of an image manipulation. I try to stay away from that. I only rely on cropping. That's it. Okay, so that's why I'm cropping these into this size. And then what happens when you divide this into 256 by 256 tiles, you get 6 tiles from this image. And from this image, you get 2 tiles. And these are all large ones, the last ones here. And from this one, I'm going to get 40 tiles and 56. So overall, I'm going to get about 1,305 images of 256 by 256. That's not bad. That's not really small data set, but small enough for these type of applications. I mean, remember, we have 6 different classes and only 1,300 images. So that's pushing it. Okay, now let's get to the code. And what am I doing here? I mean, import OS to basically walk through the directories, get the directory names, right? CV2, OpenCV to read images. NumPy, obviously, to manipulate arrays. Plotting. Patchify is one important one where I plan on dividing the images into smaller patches. And using Pillow. Why am I using Pillow? In case you would like to perform the cropping operation, resize operations, it's much easier with Pillow library than playing with NumPy arrays. Okay, so I'm going to use Pillow for that. And I'm also importing something called segmentation models, a library called segmentation models. And this is optional. The reason I'm doing that is later on you see that I use regular unit, but at the same time, I also wanted to use a pre-trained unit like a VGG backbone with some ImageNet weights or something. So segmentation model library makes it easy for us to work with those type of models. Of course, TensorFlow.keras.metrics, I'm going to get my mean IOU value so I can have a quick look at what my IOU is. And more importantly, the numbers, the pixel values go from 0 to 255. You have a choice of dividing each pixel value by 255 to scale them between 0 to 1. Here I am just choosing to use min-max scalar or standard scalar. I'm importing both. I'm going to use min-max scalar because I'm going to set my scalar as min-max scalar. Okay. The next thing, let's define our root directory. Our root directory is semantic segmentation dataset, semantic segmentation dataset. That's my root directory. And within that root directory, I'll walk through each subfolder and extract the images. Okay, like we have done many times in the past videos. I'm defining my patch size as 256 here because I'm going to divide these images into 256 patch size. Okay, so far that's it. Now the next part, I'm going to load the images, and after that I'm going to load masks. I'm going to perform very similar operations between images and masks, but let's go through the image part. Okay, so for path subdirectories files in os.walk, I mean, basically I'm walking through this root directory. In case you don't know this, let's just go ahead and do that and print. So you see, sorry, I just showed you all of these and I did not run any of these. So there you go. Let's go ahead and start the code. And I just want, I mean, again, this is very basic, but for those of you who haven't explored, glob or OS, this can be a good quick crash course in this. Okay, let's go ahead and run these lines so you can see what am I printing. I'm just printing the path here. I'm extracting 3 things here: path, subdirectories, and files. So the path, you see how it's actually printing path to each every one of my subdirectories right there. Tile 1 images, tile 1 masks, tile 2 images, tile 2 masks, and so on. Okay, and you can also just do one more thing before we move on. Again, I'm sure some of you are getting pretty bored because you may know this, but again, here I'm just printing out every file that's present by walking through these directories. Okay, so let's comment this out and let's go down to, okay, now let's define our directory name. What's our directory name? Which is basically our os.path, and then split it. Sorry, I'm spending a lot of time explaining the basics, but again, these are the questions that most of you ask as part of the comments, so I may as well talk about it right now. So here I'm just basically separating this to get the directory name, right? Okay, right there, tile 1, tile 2, tile 3. And you may want to add a print statement next to this and then understand what's going on. If you have any questions, print statement is your friend. Okay, go ahead and print right there to get a good understanding of what's going on. Okay, so this part, I just want to read images, nothing else in this part of the loop. So if directory name equal to images, meaning when you do this split, it's going to split this at images or masks or nothing or images or masks. I'm saying here, if the directory name is images, now my images equals to that directory path. And then now within that directory path, look for anything that ends with .jpeg, right? These are our input images, and go ahead and read that image. Very basic stuff, but thanks for your patience, some of you advanced coders, but you can appreciate we all went through this learning process, right? Okay, I'm using CV2 to read the image, and I'm reading the image in RGB, okay? Because our images are in RGB. And then I'm cropping these images, okay, to a size that's nearest to whatever the size is divided by the patch size. So if the image is, I don't know, 770 by something. So all I'm trying to do here is, what is 770 divided by 256 multiplied by 256? So it gives me, okay, this is like the scaling factor for X, scaling factor for Y. That's exactly what I'm doing. I should have called this scaling X and scaling Y. And when I convert my image into pillow image, I'm going to crop from 0, 0 to scale in X and scale in Y, right? Size in X, or not scaling factor, sorry. I'm getting the nearest value that's divisible by 256. So size in X and size in Y. And I'm capturing this, converting this into a numpy array, and then a couple of print statements right there, okay? I mean, a single print statement right there. So up to this point, what do I have? Up to this point, what do I have? I have a large image that's resized. I think let's run this. Let's just run this. It's very important. Image. Let's just run up to this point, okay? So you can see I'm going through the loop, but I really want to make sure you understand this. Okay, look at my image size, 1479 by 2049 by 3, right? This is the image size for the last directory there. But that's not good enough. So let me go ahead and define my size X and size Y. My size X and size Y. Let's run these two lines. Size X is 2048, size Y is 1280. What this is telling me is, instead of 1479, I want this to be 1280. Instead of 2149, I want this to be 2048. That's all, okay? These two lines. And then I convert my input image into a pillow image object, and then crop that from 0, 0 to whatever size X, size Y is. So when we do that, our final image size, and let's convert that back into numpy array. When we do that, our final image is just 1280 by 2048. Okay, so all these operations to get there. Now what? Now let's go ahead and take that large image, 1280 by 2048, and patchify into smaller images of size 256 by 256. That's exactly what I'm doing here, using patchify library, applying that onto my large image to get a size of 256 by 256 by 3 at a step size of 256, meaning no overlap at all. 256, 256, and keep moving. Okay, so this is the patch size that I'm trying to extract. So when I do that, you'll see that my patches underscore image is basically 5 by 8 by 1. Well, ignore that one for now, by 256 by 256 by 3. That one is added by patchify because it's going through each image and extracting those, okay? We'll drop that in a second. There you go. So 5 times 8, 40. So I have 40 images, each image 256 by 256 by 3 in this large image. That's all this is doing, okay? Now what do we do? For each of these images, 5 and 8, okay? My single patch is just drop this one, drop this, just get 256 by 256 by 3. And then I'm going to fit transform the scaler. Remember, we are scaling using min-max scaler. So I'm scaling my each patch, I'm extracting there. And then I'm basically dropping here this extra one that I have, and then adding it to my image dataset list. That's it. I hope you're still with me here. Okay. Next part is doing exactly the same with masks. Okay. The only difference, I have a couple of lines different right here. And everything is same right here. I mean, of course, my masks are .png, not JPEG, so I changed that right there. But more importantly, in OpenCV, when you read images in color, they're read as BGR and not RGB. For visual purposes, when we print it, it would be nice to see these in the same color. So I'm converting my BGR to RGB. That's the only addition that I have made here. Otherwise, everything should be exactly the same. All I'm doing is taking a large image, cropping them to the same size, images and masks, and then chopping them into 256 by 256 by 3 size, and then just adding them, capturing that into a numpy array. Now, if you have images, a whole bunch of images that you have in a different folders, please watch my videos on using data augmentation to read them directly from the disk. Okay, right now I'm going to store them here. Okay, let's run this. After all that talk, where did we end? Let's go ahead and run all of these from here up to the point where we have yeah, right there. And I have this print statement, so I know exactly which image is being done. So tile 5, tile 6, tile 7. It will be slow in tile 7. These are all large tiles. And tile 8. And now it's going through masks, doing exactly the same. Okay, initially it was images, now it's doing the masks. At the end of this, we should see image dataset is a list of 1305 individual numpy arrays. Same with mask dataset. Lists, not good for us. Let's convert them into numpy arrays. So there you go. That's one, that's there. So my image dataset is 1305 by 256 by 256 by 3. Now I'm all set, almost ready. But we need to take care of these masks. We don't know what the labels are. That would be the next point. Again, if you watch my videos on a regular basis, you know how paranoid I get whenever I do these type of operations. I just want to make sure my images and masks are matching. There's so many times you do a small mistake and then your images masks are not aligned, but then you try to train a model and you're like, oh, why is my model not converging? Yeah, because your masks and images are not aligned. They're not the same. So in this case, they are aligned. Wow, a nice golf course in Dubai. Okay, so let's look at the next one. The next one, I'm just showing some random images just to make sure, okay, everything seems to make sense. This is a tough data set, I can see. The road in the sand, barely visible, okay? These roads are pretty nicely visible. Okay, so we got the point. This road can be a bit challenging. And that road, it's not even labeled, so maybe we don't have to worry about it. We'll see how the model performs. So far, so good. Now let's tackle the masks. Okay, so let's start by looking at RGB to hex. I don't know how many of you raise the hand if you know what hex code is. So hex is hexadecimal base 16, as you probably know, those of you who raised your hand. And how do you get base 16? Well, the number is divided by 16, okay? And ignoring any, let's take an example. Instead of reading this, let's take an example. For example, one thing you need to note is the way it's representing in hexadecimal is 0 to 9, the number 0 to 9 or 0 to 9. And the numbers 10 to 15, this is hexadecimal, meaning it goes from 0 to 15, right? So 0 to 9, 0 to 9, and numbers 10 to 15 are given values, labels of A to F. So when you look at an RGB example where you have red as 201, a pixel value of 201 in the channel of red, how do you convert that to hex? Well, divide this by 16, right? This is base 16, divide by 16. 201 by 16 equals to 12 with a remainder of 9. So this is represented as, where is my 12? 12 is what? 12 is A, B, C, C, right? So this is represented as C9, okay? So C, because that's what it's divisible by, and 9 is the remainder. So now hopefully things make sense. So if you look at RGB from hex 3C1098, what is 3C1098? 3C1098 is the code for building, 3C1098. So all I'm trying to do here is finding out what RGB is for building. Otherwise, I don't know, and maybe some data sets you already know, but in this case, I don't. So I'm trying to do this exercise. So 3C1098, how do you get red, green, and blue values? Okay, 3C, 16 times 3 plus whatever the C is, 12, which is 60, right? And these two correspond to red, these two correspond, oh, I messed it up. And these two corresponds to green, these two corresponds to blue. Remember, hex code is still representing RGB. Okay, let's look at 10, 1, 0. This is 1 times 16 plus 0, so the value is 16. Let's look at 90. 9 times 16 plus 98. Sorry, I made a mistake there. Okay, 98. 9 times 16 plus 8, which is 152. So 3C1098 is nothing but R value of 60, G of 16, and B of 152. Again, I know I'm going at a painfully slow pace, but I want to make sure there is no gaps here, so we can minimize the number of comments asking for help. Okay, that's the motivation here. You don't have to hand calculate that. There is a way Python actually handles. For example, if you have 3C, go ahead and type int 3C and 16, and let's go ahead and see print A. Okay, so if you type A equals to int 3C16, and then if print A, you see that A is nothing but 60. So when you do int 3C and 16, Python knows that, hey, you're asking me to convert 3C into a of base 16 into an integer, and it returned a value of 60. So we're going to use this to convert each of these into corresponding RGB values. So all I'm trying to do here is, you see, for my building, okay, what is my building? My building is this 3C1098, where I stripped off the hash, which is just 3C1098. So for my building 3, okay, of base 16, this is basically, this part is nothing but that part, okay? And do that for 0, 2, and 4, which means do that for this, and for that, and for that, and capture that into a numpy array. Let's go ahead and run this and see what we get for building. So let's go ahead and print. Okay, building right there. You see, we got 60, 16, 152. That's exactly what the RGB code is for that. Let's do that for land, road, everything right there. And let's get a dummy label, like one of the labeled images that we just loaded. Why am I doing that? So I can open it and look at the third channel. So now if you look at this pixel value right there is 110, 193, 228. What is 110, 193, 228? That's a road. So this is representing a road right there. Okay, this part right there, that's representing a road right here. Okay, I think we are slowly getting there. Please be a bit patient right here. So far, all we have done is getting a good understanding of what each of these hex values represent. Now we need to convert those individual RGB, pixels into some sort of an integer, and eventually to one hot encoded. That's what this part actually does. What we're trying to do here is, I'm saying, create an empty placeholder numpy array with all zeros of the same shape as my 256 by 256 by 3, and then fill the values wherever the label is equal to building, meaning we just know what the building is, right? 60, 16, and 152. If the pixel values are that, then replace them with a value of 0. If the pixel values are equal to land, well, which is something else right here, 132, 41, and 246, replace the value with 1, and the next one 2, 3, 4, 5, and so on. So this is the function that actually converts your RGB into a 2D label. Okay, and let's go ahead and run the function and then apply it to our labels right there. Okay, so let's go ahead and do that. Now our labels channel, or labels numpy array, which we'll see in a second, will have only 256 by 256, and the 3 is dropped. Okay, and then we are going to expand the dimensions. So if you look at the labels, I have 1,305 images. We know that 1,305 masks, each 256 by 256. The 3 is dropped because we converted the 3 RGB into values of 0, 1, 2, 3, 4, 5. So here you can see all ones right there. Okay, now let's go ahead and expand the dimensions at axis 3. So we have something that's ready to be fed into my deep learning or UNet network. So far, so good. Again, I get paranoid whenever I do something like this. So let's go ahead and print all the unique labels in our data set, in our masks, which is what we call labels here. So np.unique gives you all the unique labels, and our unique labels are 0, 1, 2, 3, 4, and 5. So good. So far, so good. Again, my paranoia kicking in. So I'm going to plot my images and masks just to again confirm that nothing got messed up while I'm doing all these conversions. So everything looks perfect. Okay, now let's go down to the next step, and then you're all set. The next step is, hey, so far our labels are not one-hot encoded. They are integer encoded, meaning every pixel has an integral integer value 0 to 5, representing each class. We need to convert that into one-hot encoding or to categorical. That's exactly what I'm doing right here. Okay, so let's do that. And I covered this extensively many times, so I'm not going to talk much about this. So once you're done with that, my labels that are categorical, you see 1305 by 256 by 256 by 6. 6 again corresponds to 0, 1, 2, 3, 4, 5. But in this case, they are one-hot encoded. So all values are going to be 0 or 1. That's it. Okay. We have everything ready. Let's split my data and labels into xtrain xtest, ytrain ytest. So you have your testing and training. From this point on, I'm pretty sure most of you know how to handle. This is standard multi-channel or multi-class unit. That's it. Okay, and you can use your own approaches. At this point, you can do various types of experiments like what I have done. Here, I experimented with calculating weights, meaning all classes are not balanced. So you can, one of the loss functions you can use is dice loss, where you can provide class weights as a list right there. And you can compute the class weights and provide the class weights. Okay, so these are all things that you can experiment to see how well the model is performing under different conditions, because I cannot guess anything, at this point. At this point, it's up to you to experiment with this. So let's, I'll leave bulk of that to you, but let me just show you a couple more things here. So first of all, I'm just weighting everything equally. Why 0.166? Because I have 6 classes. 1 over 6 is 0.16666, and so on, right? So I'm equally weighting, which should work fine actually. And then I'm going to use a total loss as the loss function. A total loss is a combination of dice loss plus focal loss, okay? And dice loss is think of this as intersection over union, very similar to that. And focal loss, I think I did a video on the topic of focal loss. Go ahead and check it out. It can be very useful for data sets where you have easy to segment classes against tough to segment classes. Okay, so this is what I have, and then the next part is, let's go ahead and get my image height, width, and channels. Why? Because I'm going to provide those as input shape to my unit. Okay, so from simple multi-unit model, import multi-unit model. We have used this a couple of times in the past videos, but just for the sake of completeness, let me show you. This is the plain vanilla unit as reported in the original paper, except I added dropout. That's pretty much it. Everything else is very similar. Okay, I also added a function here for Jacquard coefficient, which is similar to IOU, intersection over union, right? You have your true and predicted, and we are just doing intersection over the union. So I'm going to use Jacquard coefficient as one of the metrics I'm tracking during the training process. And here, like I said, image height, width, and channels are going to be the inputs. And number of channels is something we'll provide, and then how many output, how many ever classes we have. In our example, we have 6 classes, so 6 outputs. I'm not going to compile the model here. I'm going to compile it outside because I'm experimenting with various loss functions and all that stuff. Okay, so this is just a plain vanilla unit. So let's go back and import what we have over there. Right there, I'm importing both the model and the Jacquard coefficient. Okay, now my metrics, I'm defining them as accuracy, which is what you typically do. In addition to that, I'm also tracking Jacquard coefficient. Now let's define a function to get the model, and this requires how many classes, my image height, image width, and number of channels, right? I mean, those are the ones we need to provide. And let's define the function, and let's go ahead and get the model. Okay, so now it's getting this model, and then we have to compile it, right? We have to compile it with an optimizer, loss, and metrics. So I'm using the standard Atom as optimizer, and then loss, I just mentioned about total loss, and metrics, the metrics we're tracking are these two. I'm also experimenting. I have experimented with using categorical cross entropy and all that stuff. Okay, so let's go ahead and compile the model and just print the summary. There you go. So the final, we are going to get the output as 256 by 256 by 6. Okay. In case you need another sanity check, you can go ahead and I think it's let's just do model dot let's say input size. Input size, is it sorry, input shape, not size. There you go. So if you wonder, is it really, what's the input shape it's expecting? Again, another sanity check. It's expecting number of images, each image 256 by 256 by 3, okay? And you can also print out the output shape exactly the same way. Okay, all the sanity, everything is done. We made sure that everything is working fine, and at this point, I can go ahead and fit it. Model.fit, extrain ytrain with a batch size of 16. Again, you can change any of these right here. So let's go ahead and run these. I'm doing this for 100 epochs, and you'll see that, again, I have a GPU to accelerate the training. And I hope you watched my video on how to get your Windows system ready for your, GPU, especially using TensorFlow and Keras. Now, while that's running, let me just show you this is all my nodes running different experiments over there, and you see how this is running. Yeah. So the standard unit takes, in this case, it's pretty fast. It's taking, let's see, probably like less than 20 seconds per epoch. So this should be done in a decent amount of time. And if I use different models, 40 seconds, that's slightly, but let's wait for the second one. I'm already getting 68% accuracy, and my Jacquard coefficient, think of this as IOU as 36% right there. I believe it peaks at about 75% IOU, which is excellent for this type of, for smaller data set, 6 classes. About 12 seconds, yeah, that's not bad. Here is another model. I'm not going to run this right now, but this one is using segmentation models library that I mentioned earlier. Here you can actually use ResNet 34 or VGG, whatever backbone you would like to use, with ImageNet weights, and go ahead and run this and see. I did not see much improvement using this versus what I'm doing right now, except using this converges a bit faster than the other approach. So I think the other approach, about 75 to 80 epochs, I get about 74, 75 per IOU. And for this one, it reaches 72, 73. Did I write down anywhere? It reaches the 72, 73 IOU within like 30, 40 epochs. That's the only difference right here. Okay, I didn't see any improvement in the overall quality. Now, let me go ahead and stop this because I've already done this. And let's look at this part. Actually calculates the IOU. One thing I should mention is when you're loading a trained model for inference, for predictions, you can just ignore all of this and just say compile equal to false, because you don't want to compile you don't need to compile your model. If you want to open a pre-trained model to continue the training process, especially when you're using your own custom loss functions and custom metrics, it's going to throw an error saying, hey, I don't know what you mean by, let's go ahead and run this line so you know what I'm talking about. Just a second. So it's going to throw an error saying, I don't know, unknown loss function, dice loss plus 2 focal loss. What do you mean by that? That's exactly why I have added these two lines. Sorry, I have added these two lines. My custom objects are dice loss plus 2 focal loss, because it's saying that it doesn't know what that is. It's basically the function that I defined earlier as total loss. Also, it will throw an error saying, hey, I don't know what Jacquard coefficient is, and then go ahead and define that. So once I have it, it's going to let me load the model, and now I can use this model for further training. I can go back and train this more. Okay, that's all. That's the quick side note. Okay, now let's go ahead and predict this on a few images so you can see this in action. All I'm trying to do here is, again, get some test images and some test masks, and go ahead and predict on the test masks. Of course, when I predict it, let's run this one by one so you can see exactly what we mean. When you predict it, it's going to give you, oh God, yeah, I haven't Let's go ahead and do these lines. Again, they're all self-explanatory, so I don't want to waste your time talking about those things. If you have, again, questions, it says, okay, something is happening with my memory, but let's see if it works. So let's go ahead and do the prediction. And when you do the prediction, it's going to show you the prediction as 6 channels, right? I mean, this is 1 hot encoded. So we need to get it back into the integer encoded. That's exactly what I'm trying to do right there. Integer encoded, and then now we can go ahead and plot it. So let's go ahead and plot that image. And this is, I mean, again, the colors are not identical. That's because we haven't changed the colors of this predicted image. I'm just using pyplot, that matplotlib.pyplot to just show this image. So it's just showing it in whatever the default color scheme is. But just pay attention to the segmentation. That's not bad, actually. That's actually doing a good job on this image. We'll change these colors in the next video, by the way. And then let's do a couple more images. It's not always good. You'll see some bad ones like this, obviously. Yeah, you see how this is actually doing a nice green and this is confused. So this is not a great one. That's sometimes I like what my model is doing compared to what these guys actually are showing right there. Yeah. You see, so it's doing good. It's not doing good on some. So this is only 100 epochs. Try 200 epochs, and so to see if there is any improvement. On mine, it wasn't improving that great after the first 100 epochs. So I stopped it. Again, experiment with this. So I hope now you learned how to handle this. The main important point is how to pre-process the data and then use unit to do the predictions. In the next video, I hope you'll stay tuned for that one. We are going to take this trained model and then predict on individual patches, put the patches together. Very easy, few lines of code because someone else already did the bulk of the work. I'll just show you how you can take an existing library that actually has some bugs in it, but I fixed the bugs. I'll share the code. And you can put the patches together. So when you get this grand big image, it's all smoothly tiled. You don't see any tiling effects or anything. Okay, so please stay tuned for the next video. Thank you guys, and subscribe.